Alrighty. Okay, so. Alright, guys. So, my name is Nikhil Tandon. This is the first part to our homework 3. It's about next generation computing. So, the topics we're going to go over for this part 1, it's going to be biocomputing, and then that's a list of what's going to be in the biocomputing, like the subsections for it. DNA computing, membrane computing, P systems, and neuromorphic computing. Second topic will be nanocomputing. The subtopics for that will be nanomagnetic logic gates, quantum dot cellular automata, and also the next topic will be spintronics. To be about quantum computing, magnetics, spin qubit, semiconductors. So the subtopics for those. And then the main topic, which is the final one, out of the 4, will be optical and photonic computing. Quantum computing will be a subsection or another part for that. Silicon photonics, reverse logic, photonic integrated circuits. Alright, so we're going to start with biocomputing. Alright, so biocomputing, or biologically inspired computing, is a major subset of the field of natural computing, which encompasses several subtopics that are not relevant to the study. Biocomputing includes a broad range of computing approaches based on biological systems, ranging from the use of algorithms such as a swarm intelligence to the membrane computing, memtic computing, cellular automata, DNA and molecular computing, neural computing, and evolutionary computing. Biocomputing has many diverse applications, including computational intelligence, bioinformatics, natural language processing, machine learning, algorithm theory, data mining, and many other areas. Alright, so the subtopics we're going to be talking about, so it might be a lot of information, but we're going to get through it. Biocomputing, and the 2 first subsections for those, so it's a DNA computing and membrane computing. So we'll start off with DNA computing, known as biomolecular computing. Molecular computing, biochemical DNA computing, or DNA computing, is based on the notion that data can be encoded as a biomolecules, such as DNA or RNA strands, and can be transformed through molecular biology tools to perform arithmetic or logical operations. Unlike biocomputing techniques such as membrane computing, cellular automata, or evolutionary computing, which uses theoretical electronic hardware, DNA computing uses molecules as hardware. DNA is used as the input into DNA logic circuits to create complicated computing systems that are programmable, precise, and efficient. The 2 advantages are, first, the one is DNA can carry significantly more data than silicon, and the second, operation on DNA are massively parallel. Okay, and we're going to talk about membrane computing now. It investigates a class of computing models known as a membrane system, or P systems, which are abstracted from the architect, structure, and functioning of biological membranes with living cells, as well as how cells are organized in tissues, organs, such as the brain as well, and higher order structures such as colonies of cell bacteria colonies. Membrane computing abstracts the compartmentalized nature of internal structures that are affected by membranes. Membranes computing is a rigorous and comprehensive theoretical framework that provides a parallel distributed framework which, with flexible evolution rules. It has been applied both in the field of biology for activities such as modeling photosynthesis, signaling pathways, cell-mediated immunity, as well as in computer science for graphics, cryptography, and solving computational hard problems in the P and NP problems. The next biocomputing is P systems and neuromorphic computing. All right, so we're going to start with P systems. So a P system is a computational model in the field of computer science that performs calculations using a biological inspired process. They are based upon the structure of biological cells, abstracting from the way in which chemical interacts and crosses a cell membrane. A P system is a computational model in the field of computer science that performs calculations, all right, and they're based upon the structure of biological abstracting, okay, and interacts and crosses cell membrane. So I put that twice, but that's my fault. Maybe I did something wrong there. The P system model was introduced by Mr. Pan of the Romanian Academy in 1998, and research by him and many others have been expanding rapidly ever since. Neuromorphic computing. All right, so computing architecture and design principles that are based on the human brain is a new computer paradigm that offers an alternative to the von Neumann architects and is currently under intensive international investigation. We did talk about the von Neumann model in our first exam. One of the major goals of neuromorphic system is to build a thinking machine, as it uses hardware that resembles biointelligent systems at the physical level so that it can be more closely match how the brain works on a functional level. Neuromorphic computing devices must be engineered with both area and power efficient. Circuits that mimic neuron and synaptic behavior while supporting massively parallel connectivity. Additional essential features that have recently listed by Rajendran and Albart in 2016 are those topics right there: analog or stochastic programmability, interconnection and density, on and off ratio, and power consumption. All right, nanocomputing is the next topic. So nanocomputing is computers who have physical dimensions are microscopic. The field of nanotechnology is part of emerging field of nanotechnology. Is an emerging field, yes. Tiny circuitry that can only be seen with the aid of a microscope. Current gadgets are made of semiconductors under 100 nanometers in length. Nanocomputers work more storing in quantum dots or spins. Nanomagnetic logic and logic gates. So we learned about logic gates in class, but these are including or incorporating nanocomputing. All right, so nanomagnetic logic is an energy-efficient computing architecture that relies on the dipole field coupling of neighboring magnets to transmit and process binary information. In this architecture, nanomagnetic chains act as local interconnects and extensions of QCA, and can be viewed as a magnetic implantation of QCA, where information signals are processed through magnetic field interaction in nanocells. As such, it is also known as field-coupled computing, or previously known as magnetic QCA, while an electronic-based version of QCA is susceptible to size variation. Nanomagnetics, which exhibit a collective spin behavior, are more immune to structure variations. Logic gates, which is basically implementing Boolean functions or logic operations performed on one or more binary inputs that produce a single binary output. So, and, or, nor, not, and XOR is another one that we covered in class. But we also took a quiz on it. So, yeah, so we're all familiar with that. All right, the next topic for nanocomputing is quantum dot cellular automata. That was a QCA. If you saw it on the last slides, I talked about QCA. This is what they're referring to. So QCA are based on the simple interactions rule between cell placed on a grid. A QCA cell is constructed from 4 quantum dots arranged in a square pattern. These quantum dots are sites electrons can occupy by tunneling to them. It consists of 4 quantum dots. You see 1, 2, 3, 4, and also the 4 squares as well, and 2 electronic changes. Under effect of the force of Columbian repulsion, These two electronics can be placed only in two quantum sites diametrically opposite. All right, spintronics. It's our another topic that we were referring to. I just want to check one thing. All right, so this is the third topic for our part one. All right, so spintronics, known as a spin electronic of fluxtronics, is the study of intrinsic spin of the electrons and its associated magnetic moments, in addition to its fundamental electronic charge. In solid-state devices as well. And spintronics differ from older magneto-electronic in the spin that are manipulated by both magnetic and electrical fields. The spintronics dataset has 562 records between 2013 and 2016. Alright, so I'm just going to skip that part. So it's when an electronic is placed in a magnetic field, it spins, polarization become bistable, which can be used to encode the logic bits of 0 and 1. I just wanted to skip that part because if you will go back to my slides, you can definitely read that. I don't think it's necessary to read at the moment because pertaining to the topic, it's just a little too much. And then this is a picture of magnetic and electronics due to spintronics and how they're similar and how they're different. All right. The next two topics for spintronics is quantum computing and magnetics. So we're going to start with quantum computing. Quantum computing is a study how to use phenomenon in quantum physics to create new ways of computing. Quantum computing is made up of qubits. There's another topic about qubits, so we'll definitely get into. If I sneeze, I'm sorry about that. But unlike a normal computer bit, which can be 0 or 1, a qubit can be either of those, or a superposition of zeros and ones. Quantum computing is the new generation of technology that involves a type of computer 158 million times faster than the most sophisticated supercomputer we have in the world today. So quantum computing in the future is definitely going to be a biggie for us, and it's going to be our supercomputers. Yep, so magnetics is basically 3D magnetic ratchet. This was part of the slides, in the PowerPoint. I really couldn't find that much about magnetics for this topic, but I did find it in the textbook about specific 3D magnetic ratchets. They move from 2D to 3D architecture, thus enhancing density and power consumption. Shifts magnetic kinks solution from one magnetic layer to another in a transistor less. While this approach offers a direction for 3D microchips in the future, the technology is far from that stage due to technical challenges such as a variation in magnetic layers, dipole fields, data retention, lifetime, and reading and writing solutions. Spintronics. So we were talking about qubits, and so spin qubits and semiconductors. Semiconductor is pretty easy. It's just basically just hardware that's used for spintronic material. But yeah. Spin qubit is a quantum computer based on controlling the spin of charge carriers, so electrons and electron holes in semiconductors. So they definitely go along with each other. That's what I was referring to, like the hardware, how semiconductors is incorporated with spin qubits. In this device, two quantum dots, each with only one electron inside, are constructed side by side and tuned so that they are tunnel coupled. Information is stored in the relative spin of two electrons, further reducing and coupling of the qubit to its environment. All right, a 30 qubit quantum computer would equal the processing power of a conventional computer that would run at 10 teraflops. So a teraflop is trillions of floating points operations per second. Semiconductors is used primarily in electronic devices, including chips, diodes, transistors, and integrated circuits. I do have a list of them as well. So they also can be LED. These are a bunch of transistors that we use in certain devices you can use it for, or in our next generation computing devices or theories. Anything that computerized or used radio waves depends on the semiconductor. Alright, so optical photonic computing. This is our last topic for part one. Optical or photonic computing uses photons produced by lasers or diodes for computation. For decades, photons have promised to allow a higher bandwidth than the electrons used in conventional computers. Most research projects focus on replacing current computer components with optical equivalents, resulting in an optical digital computer system processing binary data. This approach appears to offer the best short-term prospects for commercial optical computing, since optical components could be integrated into traditional computers to produce an optical electronic hybrid. Okay, and all optical computers eliminate the need for optical electrical conversions. All right, the first two topics for optical and photonic computing is quantum computing and silicon photonics. All right, quantum computing that's connected with optical and photonic computing, or photonic computing uses light waves produced by lasers or incoherent sources for data processing, data storage, or data communication. Something I found really interesting in the article I just quoted there is Stanford University researchers have proposed a design for photonic quantum computers that use readily available components and a laser to manipulate a single atom that can modify the state of a photons in the system via phenomenal or quantum teleportation. So, are we going to have teleportation in the future? But yeah. Silicon photonics is a material platform from which photonic integrated circuits can be made. It uses silicon or insulator wafers as the semiconductor substrate material, and most of the standard CMOS manufacturing processes can be applied. Silicon photonics is advancing rapidly in performance and capability, with multiple fabrication facilities and foundries having advanced passive and active devices, including modulators, photodetectors, and lasers. All right, the next two topics is going to be reversible logic and photonic integrated circuits. All right, so a logic gate is a reversible logic gate is a logic gate that is reversible if we can recover input data from the output. It can't erase information and dissipate zero heat. The circuit operates in a backward operation, allow reproducing the inputs from outputs and consuming zero power. As the basic elements of logic circuits, logic gates are used to realize Boolean functions. All right, and then photonic integrated circuits, or PICs or PICs. All right, a photonic integrated circuit is a chip that could contain hundreds of photonic components that work with light. One of the key application fields for PICs is data communication, followed by sensing or agriculture and autonomous driving. For example, and biomedical applications such as lab-on-a-chip devices, as well as applications in the defense and aerospace industries and the field of astronomy. And this does end part one. I'm just going to do a quick water break. Alrighty. So this is the end of part one. We will be continuing to part two, where I choose two articles from one main topic and talked about those two subtopics and found articles about those two subtopics, not the main topic. All right, next generation computing, Nikhil Tandon, part two. All right, the two topics that we chose, or subtopics, is about semiconductors. That's about article one, and I had the whole, the actual, what do you call them? What's that thing called? Citation right there, and the article two, magnetics, and the citation right there as well. We're going to be talking about magnetics and semiconductors. All right, so the first article, so this was basically, it was about semiconductors, obviously, and had different parts, and how it, how this company ITRS actually got to that point of creating it. So they talked about system integration, heterogeneous integration, heterogeneous components, outside system connectivity, more, and factory integration. Just gonna check. Okay, yeah, that's what we're gonna be talking about in this specific topic in semiconductors. So, Article 1, 2015 International Technology Roadmap for Semiconductors. That's the title of this article. All right, system integration. The mission of system integration chapter in ITRS 2.0 is to establish a top-down system-driven road mapping framework for a market driver of semiconductors industry in the 2015 to 2030 period. So this is still going on to this day. This is up there, their whole roadmap, how they're referring, their whole manual of what they did, and how they're actually working on this specific semiconductor, and how it's going to be very valuable in our future. The SI, that's going to be System Integration Focus team, is currently developing and constructing roadmaps of relevant system metrics for mobile data centers and IoT devices or drivers. The mobile driver embodied by the smartphone product has redefined the existing ITRS consumer portable system on chips driver with richer feature requirements. All right, and heterogeneous integration. The mission of system integration chapter, okay. All right, yep. It's evolving and relevant system metrics for mobile data center, okay, and the mobile drivers and bodies, okay. All right, so now we're going to talk about the heterogeneous component and the outside system connectivity. Heterogeneous components identifies trends in high market growth potential applications, determines the device performance requirements that are needed to enable those applications, and uses this information to discover technology gaps that must be solved in order to produce future products that are envisioned by the roadmap. This roadmap is produced in collaboration with MEMS and sensory industry groups. So every single roadmap was completely different. So you have to pick a different layer, a subtopic, because I had to read a lot. It was each thing was 99 pages, and it took me a long time to read, but I didn't read all of it. I just read the more basic topics in the summary, just what it was actually about. But yeah, each thing was completely different, and how it incorporates with semiconductors. So outside system connectivity, it identifies and assesses capability needed to connect most elements of the Internet of Everything, IoE devices or drivers, and highlight technology needs and gaps. This includes supporting connections of a broad range of sensors, devices, and products, and to support information communication, processing, and analysis for many applications, such as mobility, energy, health, and others. It can be any type of, also for hospitals, financial institutions, stuff like that. They're helping them with their network and their security. This can definitely help them. With wireline, wireless, and optical interconnect technologies. As I was saying, any networking type of engineer would honestly need to know information about this in order for them to actually create it. So imagine their crew. There's probably a bunch of network engineers, security engineers, cybersecurity engineers, just a bunch of computer scientists working on this in order to actually discover from 2015 or 2013, I believe it was, they started it, and then it actually became a thing in 2015. That's when they started writing the article. But yeah, more, and factory integration. More is the system scaling enabled by more scaling is more and more challenged with the scarcity of resources such as power and interconnect bandwidth. Big data requirement, abundant computing and memory resources to generate services and information that clients need. So these are the requirements for more and more technologies. That's what they needed. High performance computing, targeting more performance operating frequencies at consistent power density constrained by thermal. Mobile computing, targeting more performance operating frequency and functionality at constant energy, constrained by battery and cost. Autonomous sensing and computing, IoT devices, targeting reduced leakage and variability. Okay. Factory integration. This is the final topic for this one. Then we will get to Article 2. Factory integration. The focus area of ITRS is dedicated to ensuring, ITRS, remember, it's the company that's working on this research, to ensuring that the semiconductor manufacturing infrastructure contains the necessary components to produce items at affordable cost and high volume. Realizing the potential of Moore's Law requires taking full advantage of device feature size reduction, new materials yield improvements to near 100% wafer size increases, and other manufacturing productivity improvements. This is for them, I believe, and how their integration for them, so how that's going to really assess and ascend the whole research for their specific roadmap for semiconductors. This in turn requires a factory system that can fully integrate additional factory components and utilize these components collectively to deliver items that meet specification determined by other ITRSs, by other ITRS focus areas, as well as cost, volume, and yield targets. Preserving the decades-long trend of 30% per year reduction in cost per function also requires capturing all possible cost reduction opportunities. Alrighty, we're going to be now discussing Article 2. This was a kind of a short one, but we'll definitely get into it. Alright, this article was called Magnetic Tunnel Junctions. I believe, okay, so let me just talk about Article 1 real quick. Article 1 was by, okay, it's not showing there, but I had it there definitely. It was the ITRS, so that was the company. So yeah, that's fine. And then Article 2, about magnetics, was the author were actually two articles, Zhu, I think it was like Zheng GJ, and then Park C. They actually wrote this in 2006. It's a long time ago, wow. I was a child. But okay, let's just go back to the beginning of this. Alright, magnetic tunnel junctions. Magnetic tunnel junctions, and MTJ, and we're going to give it a little short, consist of two magnetic layers separated by insulating layers. For magnetic layers that they have large pin polarizations, large resistance changes occur through the junctions when the moment of the magnetic layers switch from a parallel to an anti-parallel alignment. When two conducting electrodes are separated by a thin dielectric layer with a thickness ranging from a few angstroms to a few nanometers, electrons can tunnel through a dielectric layer, often referred to as a tunnel barrier, resulting in electronic conduction. Alright, and in this picture, it was an article, it shows electronic tunnel phenomenon arises from the wave nature of the electrons, while the resulting junction electrical conducts is determined by the evanescent state of the electrons wave function within the tunnel barrier. Yep. It's referring to the tunnel barriers right there, and how the metal is, when it goes through there, gets a little smaller, and how you know how the waves are actually a little taller, and after it goes to the evanescent state, it shrinks down. I'm going to continue on to this picture because it was very important. Alright, so electronical tunneling through a thin tunnel barrier. Okay, this is really interesting how you can actually, they measured and gave an example how electrons go through barriers. I personally was astonished when I really read this article. Alright, so the top is the wave nature picture of tunneling of the electrons. A traveling wave approaching from the left of the barrier, right? Left of the barrier, when the barrier height is greater than the energy of the electrons wave inside the barrier becomes evanescent. At its amplitude decreases, like the up and down, that's the amplitude, the range of that, exponentially through the barrier. If the barrier layer is thin enough so that the amplitude of the evanescent wave does not completely diminish at the other side of the barrier, a traveling wave reemerges again with the residual amplitude and continues to propagate. The bottom picture is the corresponding particular view of tunneling effect. The amplitude ratio between the transmitted and incident wave determines probability of electron tunneling through the barrier. Kind of the same result, it just gets smaller, or the metal reduces in size, or it just spreads out from each other. And yeah, that was basically about the magnetic tunnel junctions for Article 2. This does end the part 2 of my homework 3. And yeah, this is the end of our homework. Yep, my name is Nikhil Tandon, and I approve this message. Alright.